Hi. In the last lecture, we talked about the coupled UP formulation for solving the Navier-Stokes equation. Today, we will talk about the fractional steps method, which are an alternative approach to the coupled method for solving the Navier-Stokes equation. First, we'll start with the Choring method, which is the simplest approach among the different class of fractional steps methods. So here we're in the fractional steps method, we look at the problem in an unsteady formulation, and these methods are typically more suitable for unsteady problems. And even if you have a steady problem and you want to use them, you can formulate your problem as a steady problem and just march forward in time until you reach steady state. So therefore, in our notation, the superscript denotes the time step, U naught is the initial condition, UN minus 1 is the previous time step, which is known. And then in all these methods, we have an intermediate step, which we're going to show with U star. And then UN is the current time step, which is the unknown that we want to solve. So in the Choring method, the idea is first to compute a tentative velocity. So that's U star. And we do that by ignoring pressure. So we ignore pressure, we just solve for velocity, and then we project the velocity onto the space of divergence-free velocity vector fields using an idea similar to the pressure Poisson equation. And then finally, we update and correct the velocity. Okay, so step one is a tentative velocity. I take my Navier-Stokes equation, the momentum equation, and I ignore pressure. And I'm going from the previous time step, n-1, which I know, to this tentative step star. So if I do my finite difference discretization in time, so I have U star minus UN minus 1, and then the advection term, I can evaluate that at the previous time step, so that to make this completely known. So the U here is valued at the time step star. So that's your tentative velocity, which is unknown. And the force, if you have a force or your boundary conditions, they can be evaluated at the current time step. So to derive the weak form, the test function is V. In our notation here, we multiply both sides of this equation by V. We leave all terms as it is. We just perform integration by parts on the diffusion term, as you've seen multiple times. So this is what we get. I've taken it to the left-hand side, so that's what the sign becomes positive. And you can impose boundary conditions for velocity. So here in the weak forms, I'm going to be this lecture, I'm going to be ignoring any boundary term just for the simplicity. Okay, so in this case, if you look at this weak form or this equation, the goal you solve for U star, and UN minus 1 is known from your previous times. And you also impose any boundary conditions when you're solving this equation. In step 2, we basically go back to the momentum equation. Now, this time, we only keep the pressure which we previously ignored. Okay, so this is what the momentum equation Navier-Stokes becomes. And we also keep an eye on the continuity equation because we know pressure is tightly connected with incompressibility. And we march from step star, which is our tentative step, to the actual step, time step that we want to find, which is time step n. So if I write these two equations here, partial U partial t plus gradient of p equals 0. If I do my finite difference, going from star to n, this is the equation that I find. Note that un is unknown, pn is unknown. So n is our current time step that we want to find. U star is known from the previous step. And I also have my continuity. Now, what I can do is I can take the divergence of this equation, and I get something very similar to the pressure Poisson equation we previously talked about. So by taking the divergence, this is what I get. So divergence of UN minus divergence of U star divided by delta t. So divergence of UN is 0 because of my continuity equation, right? I want my velocity at all time steps to be divergence free. So this just becomes 0. Divergence of U star is not necessarily 0 because when we solved this equation, we ignored pressure and we didn't impose incompressibility. So this is actually not 0. So this stays here. And divergence of gradient of pressure, that's my Laplacian operator, right? So Laplacian of pressure. So this is the equation that I get. It looks like a pressure Poisson equation. You have Laplacian of pressure at the current time step that you want to find. equal to divergence of U star divided by delta T. The right-hand side is known from the previous times. Okay, so you solve this equation to find the pressure. And the weak form, you multiply both sides by Q. Q is a scalar test or weight function corresponding to pressure. You multiply both sides by Q. This is the Poisson equation that we've already worked on earlier in this course. You just do integration by parts here. That gives you this minus sign, and you give the derivative from P to Q, which you multiply this term by. And the right-hand side is just a source term. You just leave it as it is. So now in this step, you find Pn. So P, the pressure at the current time step, is what you find, and U star is known from the previous step, step 1. Now, final step is that, okay, I found Pn, I found the necessary pressure that's required to make the flow incompressible. So I found my pressure, but now I need to also find the velocity, because so far I haven't found Un. Un, when I took the divergence, it went away, right? So I only have U star, which is not useful. It's an intermediate velocity and not non-physical velocity. So what I do is that I go back to this equation that I had, the momentum equation with only pressure. I take a look at it. I see that, okay, U star I know from step 1. Pn, I just found it in step 2 by solving this pressure Poisson equation. So the only unknown that remains in this equation is Un, right? My velocity at the current time step. And this is actually trivial math, right? So it's nothing fancy. Just this is known, P is known. You can take its gradient, take it on one side, and then you find Un. And you can do this in a weak form formulation as well. If you multiply both sides of this equation by V, this is the corresponding weak form to this final step where you find your velocity. And the pressure, you already know it from step 2. Okay, so this is the summary of the Choring method. So these are the 3 steps we had. So here, this bracket notation represents inner products that we have in these integral equations. So we have step 1, finding a tentative velocity by ignoring pressure. In step 2, we solve this pressure Poisson equation, where the velocity, tentative velocity from step 1 acts as a source term. Then we find the pressure that's necessary for us to enforce incompressibility. And then in step 3, we go back to the same equation, but now this time pressure is known. So this goes to the source term. And then U star is also known. So we just find Un, which is solution at the current time step. Okay, now the Choring method is actually the simplest fractional step method that you can use. There are more advanced versions of the Choring method, which turned out to be more robust and more accurate and better suited for more complicated fluid flow problems. And one of the most common ones is the IPCS method, incremental pressure correction scheme. So the idea here behind IPCS is that we want to keep the values for pressure from the previous time step to have a more consistent pressure correction or more accurate pressure correction method, kind of like the consistent pressure Poisson equation, if you want to make an analogy. So step 1, the tentative velocity step, is exactly the same as what I had in Choring, but now I'm going to keep pressure, but I'm going to keep pressure from the previous time step. So this is minus grad P from time step n-1, which I already know. So here, this will basically, when you derive, the weak form will be the same as step 1 of Choring, but this grad P n-1, you can merge it with the source term, right? They're really just the right-hand side term that you know. So here, Un-1 is known from the previous time step. Pn-1 which is our new term here, is known. And then we find U star, which is our intermediate tentative velocity. Then we want to find the pressure that enforces conservation of mass and divergence free condition. So here, if you look back at the pressure Poisson equation that we derived for the Choring method, we're going to use the same method. But now what we're going to do is that instead of using pressure here, we're going to replace that with the pressure increment delta P. So this is Pn, pressure at the current time step, minus pressure at the previous time step. So here I have Laplacian of Pn minus Pn minus 1 equals to the right-hand side, which is a known source term. If I take this Laplacian of Pn minus 1, which I know from the previous time step, to the right-hand side, this is the new pressure Poisson equation that I have. So this is again a Poisson equation. You have Laplacian of an unknown scalar field, Pn equal to some source term on the right hand side, which you know. In this case, divergence of tangential velocity, which you know from step 1, as well as a new term, which is now included in the ICPS method, which is Laplacian of Pn minus 1, which comes from the previous time step. So here Pn minus 1, U star are known, and you find the pressure at the current time step. So step 3 is the correction step. So in Choring method, what we did was that we went back to this equation, partial U partial T plus grad P equals 0, and we just solve for UN because now we know pressure. But now here we do the same thing, but again, instead of P, we're looking at the increment of P, delta P. So Pn is replaced by Pn minus 1. Okay, so if you look at this equation, it's, again, similar to step 3 of Choring. So this stuff U star so the only unknown is UN that you find. So basically, U star here from step 1, Pn you found from step 2, Pn minus 1 from the previous time step. So this increment that we're including is not really causing any trouble for us. It's just known from the previous time step. So it's just adding something to the source term right-hand side of the weak form. But this way we can get a whole lot of increased robustness and accuracy. Okay, so this is a summary of the ICPS method where we have these 3 steps, very similar to the Choring method, but we look at pressure increments. So we also account for the pressure at the previous time step. And if you want to see a sample of this, if you look at my FEniCS tutorials on my GitHub, you will, and I'll provide a link in the description box. You can see examples of implementing ICPS method with FEniCS. For example, the Oasis software package, which is one thing I go over, uses the ICPS method for doing a CFD simulation, which you can check it out if you're interested in using FEniCS. And also in Oasis, the software package for doing ICPS with FEniCS, it actually uses a more robust time integration. So here we are just using a simple Euler method for time integration. But if you look at the Oasis reference, you will see a more robust time integration, a higher order accurate, a more accurate time integration scheme that I believe mixes Adams-Bashforth with Crank-Nicolson to achieve second-order accuracy in time. So I will also include the paper for Oasis at the description box below, where you can see how you can achieve more accurate time integration schemes in the context of ICPS.